Hello there. We are discussing section 3.2, concavity and points of inflection. The goal is to, in this first video, discuss concavity and use the sign of the derivative, the second derivative, to find intervals of concavity. So first, just this notion, concavity in general is basically curvature. So whether the graph is curved up or curved down at a point. So if we start with some function that we could take the derivative of, basically we say, okay, it's concave up, and we're just defining this to mean if the derivative is increasing. It's easy to skip over the words here. So we're not just saying that f is increasing. It's not just headed uphill. It's that the derivative itself is increasing. So this could mean that it's getting steeper and steeper uphill. That's kind of the easiest one to think about. But it could also mean that we're on the downward slope. So in this case, the derivatives are increasing because the slope over here is more negative than the slope over here. So as we move to the right, the slopes are getting less negative. That's one notion of increasing. If you're sort of clawing your way up from the negative values, then that's also increasing. So in either of these cases, the function is considered concave up. Concave down is the other side of this, and we should consider both cases as well. We could be just plummeting faster and faster. That's a decreasing derivative. But we could also be on the upward swing, just not quite as fast as we go along. So this could be kind of a diminishing returns sort of notion. So those are two definitions, concave up, concave down. Let's try this out just from a picture to begin with, rather than jumping into a function. So here's our graph. This is all we've got. We don't have a formula for it. And our job is to approximate intervals of increasing, decreasing, concave up, concave down. So we don't, just a reminder, of course, we're just guesstimating from this picture because we don't actually have a formula. And actually that's the advantage of calculus in general, is that when we can compute derivatives, we can figure out these exact intervals where things are headed up, headed down, or curved up or curved down. So let's try increasing, and we'll recall that increasing just means we're looking for where the graph is headed uphill as we move to the right. So here we're headed downhill until we get down to the bottom here, and then it sort of slopes back up. So there's a reasonable argument that anywhere on the right side of this graph, from 0 up to 4, again, we're talking about x values, 0 up to 4, the function's increasing. Decreasing, we should consider the same thing, but that's just the left half of this graph. So we could say f is decreasing from, in this case, -4 up to 0. So there's our summary. Increasing from 0 to 4, decreasing from -4 to 0. So let's think about curvature, or concavity now. So concave up, we're supposed to look basically for where this picture looks like an upward curved parabola. So whether we're on the downward swing or the upward swing of a parabola, if it's curved upward, it's going to have constant curvature, and then, or at least the same positive or negative on that section of the graph. And then the curve downward similarly, so we could be headed uphill or downhill, but as long as the slopes are getting more, are decreasing, they're getting smaller as we go, then we have a negative curvature. Okay, so we can just make a guess here, but I think maybe the thing to try to do, at least the thing that helps me, is if I pick a part of the graph and I had to pick either an upward opening or a downward opening parabola to kind of fit to it, then this part sort of requires a downward opening one, because the graph, at least here, seems to be just slightly more curved downward than it is up. But in the middle here, somewhere it changes over. In the middle section, it feels like it's more curved upward than down. And then it changes over again somewhere over here on the right. So I'm thinking parabolas because those are the creatures that have constant curvature, sort of like a line has constant slope. Figuring out exactly where this transition spot is kind of a challenge, but the claim I'm making, just because we're approximating, is that if we try to see where these two parabolas sort of change over, it's got to be somewhere in the middle here. And I can't do it perfectly, but I'm going to guesstimate a whole number just for simplicity's sake. So if we've got right at x equals -1 And then again, maybe over here at +1, we can have those curvatures changing from downward to upward. So I'm going to say it looks like it's curved down for values between -4 and 1, and then curved down again from values from 1 up to 4. And then it's curved upward in between those two values. So concave up is our first question, and then curve downward on those outward segments. So from -4 to -1, and from 1 to 4. So there's our conclusion. We'll be back in the next video to talk about inflection points. Talk to you then.